Hey friends, so lesson 2 of our kind of big long function unit in 30-1 is going to involve conversation around rational functions and their transformations. Now, in 20-1, you focused lots on rational functions, but it was all algebraic, okay? So you looked at, and really we didn't look at functions as much as we just looked at expressions, okay? And so you talked about simplifying them, and you talked about adding and subtracting and multiplying and dividing them, and that probably created some tears in your eyes. Even now, it might bring back some painful memories, and I apologize for that. In every unit, I think there's a this is going to make you cry unit. And I often say that for 20-1, rational expressions was the I'm going to cry unit because it's so heavy into factoring and fraction rules. So for those of you who I've drug up all of these negative emotions now, stay with me because I'm going to say we actually don't do a lot of that in 30-1. Now what we're going to do with 30-1 is we're going to try and really dive into the visual aspect of it. What do these things look like on a graph, okay? How do they behave as we go from negative infinity to positive infinity along the x-axis? What sorts of things are going to happen, okay? And that's what we want to start looking at today. So first of all, a quick little definition for you. A rational number is a number that can be expressed in the form a over b equals, or sorry, where b can't equal 0. So essentially, it's anything that can be written as a fraction, okay? And you know that way back from maybe grade 9 or grade 10, right? And if we can write it as a fraction, it's called a rational number. A rational function then essentially has a polynomial on the top and a polynomial on the bottom. So we say it's in the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions. And again, we have to kind of add that caveat, q of x can't actually be 0, right? And you would have done some work with in 20-1 on NPVs, non-permissible values, and stating restrictions on all of your rational expressions, okay? So which of the following would be considered rational functions? Essentially, we're looking for a fractional type thing where there's at least one variable on the bottom of a fraction. Okay, so first guy here, f of x equals 1 over x. Totally, that is the kind of the base function of all rational functions. So that is the epitome of a rational function. But yes, f of x equals, sorry, I want to get my ink on here. I can't talk and press buttons at the same time. Okay, guys can never multitask. Okay, here we go. So that one is a rational function. This guy would be a rational function. Again, it's in the shape of or in the form of a fraction, and I've got a variable on the bottom, okay? F of x equals 2 to the x. No, that's not. That's a exponential function, and we'll talk about that in a unit that's to come. This guy down here is not. That's an absolute value function, and we dealt a little bit with absolute value functions. You did them in 20-1. You had to draw them and write them as piecewise function, if that jogs your memory. And then this guy here would also be a rational function. I have a polynomial on the top and a polynomial on the bottom. Just be careful not to assume all fractions are created equal. If I wrote f of x equals, say, 3x plus 5 over 2, I don't want you to get caught to say, hey, that's a rational function. That's a straight line, right? That is actually just y equals mx plus b. It's just 3 over 2x plus 5 over 2. So when you're looking for rational functions, you have to remember that, yes, I want to see that nice, pretty fraction, but I also want a variable on the bottom. That's what makes it, that variable on the denominator, that's what makes it a rational function, okay? All right, so I'll clear my ink and we'll keep going here. I think I have these coming up as circles, yeah, okay. Okay, so what I want you to do in your book, we're going to take a look at the basic rational function y equals 1 over x. The expression y equals 1 over x is not defined for what values of x. Well, we can never have a 0 on the bottom of a fraction, right? You can't divide by 0. That's undefined. So when x is 0, I will be undefined. Okay. Now, there is a little disconnect between the table I'm showing you and the graph that you're about to draw, but there's a point in my disconnect. I want your table to go from negative 100 to 100. So that we can talk about those numbers. But then when we draw it, we're only going to draw it from negative 10 to 10, and you'll see why in a second. But you're going to pause me at the moment, and you're going to figure this out. So just to make sure you understand, if x is negative 100 and I'm looking at y equals 1 over x, that would be 1 over negative 100, right? So this should take you like 10 seconds to fill in, not even, but pause me and go ahead and do that. Okay, so you've got that done. And you've got these numbers here. Now, what I want you to notice is a few things here. So at 0, I don't exist. Great. As I approach negative infinity on the x, right? I'm going negative 1, negative 2, negative 10, negative 100. So as I approach negative infinity, my y values are getting super, super close to 0. But they're not actually hitting 0, and they'll never hit 0. Okay, that, for those of you heading over to calculus, that is going to speak of a horizontal asymptote, okay, as I approach a number but never actually am able to obtain a number, that particular number, that creates an asymptote. On the flip side of the negative spectrum, wow, that was a deep conversation. On the flip side of the negative spectrum. Anyway, as I approach 0, what I want you to notice here is my y values are shooting down to negative infinity, okay? So as I get closer and closer and closer to that does not exist, my y values, like think of it, if I had told you negative 1 over a million, which is like super close to 0, that would have been negative a million when I flip it, which would have been way, way down, right? So my y values as I approach 0 is approaching negative infinity, okay? Now, let's go to the positive realm. Again, I want to go to when x is approaching infinity first. As x approaches infinity, my y values again are getting closer and closer to 0. And so that speaks of a horizontal asymptote on that side. Then if I look at approaching 0 from the positive side, that's called a limit, by the way, when we get into calculus. But again, I won't get there yet. So when I approach 0 from the left, what's happening is my y values are shooting up to positive infinity. So actually, the way I've just done this, that is what the graph is going to end up looking like. You're going to connect those guys together, and you've got this vertical asymptote at x equals 0, and you've got this horizontal asymptote at y equals 0. Okay, so can I have you pause me for a sec and draw that into your book for those of you playing along at home? Okay, now I'm just going to clear this and I'll show you my drawing. So we should be looking at something like this, okay? And so we've got that vertical asymptote at x equals 0, and we've got that horizontal asymptote at y equals 0, okay? Take note, when you are talking about asymptotes, you want to always state the equation of an asymptote. So I said x equals 0 there. You have to be careful. There's a fine distinction between when you're asked for an asymptote and when you're asked for a restriction. If I had asked you for the restriction, you'd say x can't equal 0. So you'd have an equal sign with a slash through it. If I ask you for an asymptote, you can't say x can't equal 0. That was for the English majors out there. I had a double negative there. You're not allowed to say x can't equal 0. You have to say x does equal 0 because that is the equation of that forbidden line, okay? Likewise with the horizontal asymptote. So when you are writing equations for asymptotes, they have to say x equals something or y equals something. When you are writing equations for, or when you are talking about restrictions, that's when you would say x can't equal something or y can't equal something, okay? All right, so let's just discuss this a little further. Is the graph of y equals 1 over x continuous? Now, the definition in math at the moment for continuous is, and I said at the moment because there's a finer definition that we'll get into in calculus, but for now, the definition of continuity would be that I can draw this whole thing without ever lifting my pencil. Now, that's not possible because of that vertical asymptote. When I shoot down to negative infinity for as I approach 0 there, I then will have to lift my pencil and then go up to positive infinity to come down, right? So no, it is not continuous. X can't equal 0 and y can't equal 0, and those both cause me to lift my pencil, okay? Are there any relative or absolute maximum or minimums for y equals 1 over x? And the answer to that is no. because y shoots to infinity and y shoots to negative infinity, so there's no max or mins there. Okay. Is there a y-intercept? The answer to that is no, there is no y-intercept because x can't equal 0. Okay. A very negative response on this page. No, no, no. Okay. Are there any zeros for y equals 1 over x? Now remember, zeros and x-intercepts mean the same thing. Okay, so I'm looking at when y is 0, can I get a value for x? And the answer to that is no, I can't. If I physically tried to do that, if I substituted 0 in for y, I would end up with 0 equals 1 over x, multiply both sides by x, and I get 0 equals 1. That's not a true statement. Like, it's not possible. Okay, and then visually on the graph, we can also see, hey, no, there's a horizontal asymptote the whole way through there. So x, there is no x-intercepts there. Okay. Okay, doing awesome. You're doing awesome. Remember that the domain is the set of all possible values of the independent variable. So it's all the x values. What values of x are not allowed? We've discussed that. X can't be 0. So what is the domain of y equals 1 over x? Well, if we were going to build it in set builder notation, we would say squiggly bracket, all the values of x such that, right? And then we can say x is a member of the reals, comma, x can't equal 0. Okay, so we say x can be anything we want except 0. That's essentially what we're saying with that domain. Okay, for those of you who learned interval notation and you prefer interval notation, which if you are heading over to calculus after this course, interval notation is the way to go for calculus. In 30-1, you can go either way, and actually you have to have a decent familiarity with both of them. So for those of you who are thinking, hey, how would I do this in interval notation? I would go curve bracket, negative infinity to 0. And then I would say in union with 0 to infinity. So all my brackets are curved there because I can't be infinity and I can't be 0. Okay. All right. Cool. Oh, sorry, I still have my ink instead of my mouse. Okay, remember that the range is the set of all possible values of the dependent variable. So all the y values. What values of y will never occur? And again, that one is a y equals 0. Okay, and so the range, same sort of conversation for this guy, except that it's y instead of x. All the values of y such that y is a member of the reals. Y can be anything we want as long as it's not 0. Okay. Now, depending on your teacher, some teachers you will find will write it in this order, and some will switch these two things. They'll start and put that in the front and then say y is a member of the reals. It totally doesn't matter. Do what delights your heart. I would not mark you wrong either way, okay? And yes, math is supposed to delight your heart. For those of you who are giving me a dirty look and throwing stuff at your screen right now, yes, math delights your heart. Okay, so a vertical asymptote occurs when we are attempting to divide by 0. Okay. All right. Okay, so now what we're going to look at is transformations. So this is going to look really familiar to you. I've thrown in an A, I've thrown in a K. I've not thrown in a B here. We can deal with B, but if you think about it, B is on the front, and really I can write B in terms of A instead. So we often, with rational functions, discuss this with vertical stretches. I may throw a horizontal stretch in just to see how you do with it. But for right now, we're just going to deal with a over x minus h plus k. So a is your stretch, your vertical stretch. H is your horizontal translation. If h is positive, I'm going to the right. If h is negative, I'm going to the left. K is your vertical translation. If k is positive, I'm going up. If k is negative, I'm going down. Just remember that it says x minus h. So if h is positive 3, on the equation, it's going to say x minus 3. Okay, so remember what all the parameters above do? Yeah, I just said it all. Let's use our knowledge of transformations to work with rational graphs. Okay, so here we go. We're going to look at y equals 2 over x minus h plus 1. So what I want you to think about is I've taken that base function. Let me just draw that base function in for a sec. switch colors here so you can see. So the base function looked like that, right? Well, I'm going to stretch it vertically by 2. And then I'm going to move it to the right 8 units and up 1. So the really nice thing about that is our asymptotes actually is where we're going to start. My vertical asymptote was at x equals 0. And if I move that to the right 8 units, that's now going to be at x equals 8. My horizontal asymptote was at y equals 0. So if I move that up 1 unit, that's going to be at y equals 1. Okay, so the asymptotes are actually going to give you a really clear picture of where you're supposed to be. Okay, so here's what your graph should look like. As far as the stretch is concerned, you could, if you were drawing these by hand, you could plug a value in, like don't plug 8 in, obviously, but you could plug a value in like maybe 7 for x and then maybe 9 for x and see where that lies, okay? Because these guys are heading to the asymptotes here and here and here and here, the stretch doesn't necessarily affect that as much as the stretch would affect these points right here. It kind of affects how that curve curves, okay? And so like if you plug in a number to the left of your asymptote and a number to the right of the asymptote, that'll give you an idea of where that curve is, okay? All right, so a description of the transformations then. Well, I've got a vertical stretch of 2 about the x-axis. I've got a horizontal translation, 8 units to the right, and I have a vertical translation, 1 unit up, okay? My domain, x will be a member of the reals, but it can't equal where the asymptote is, and the asymptote's at 8. So x is a member of the reals, but it can't equal 8. My range, y will be a member of the reals, but it can't equal 1 because that's where the asymptote is. And then the equation of the asymptotes. Well, I just wrote them here as restrictions, but now I want to write them as the actual equations of the asymptotes. Now, be careful. Here's a little communication conversation. You need to state what asymptote is what. Okay, so you can't just say x equals 8 and y equals 1. I need to see vertical asymptote at x equals 8. And for those of you who are currently raising your hand and I can't see you and saying, oh, can we just write VA? The answer is no, you can't write any abbreviations, okay? Vertical asymptote, write the words down. And don't you dare spell that word wrong when I wrote it right here. There is no excuse for spelling asymptote wrong. I'm amazed at how many tests I have marked where I have said, tell me the equation of the asymptote, and then I get this phenomenally weird spelling on asymptote, and I want to say, dude, like just look right above. I wrote it out for you. So no excuse. Make sure you spell that word right. Okay, sorry, that's a tangent. I got to get my mouse back. Horizontal asymptote at y equals 1 and a vertical asymptote at x equals 8. Okay, horizontal asymptote at y equals 1 and a vertical asymptote at x equals 8. Okay, cool. Moving right along here. Now we're going to go to 1 over 3x minus 5. Now, here's a great conversation. Remember I said we look at this in terms of A. So if I looked at this in terms of A, I would say, hey, I've got a vertical stretch of 1/3 there, right? That's the same as saying 1 over 3 over x, okay? Well, if I looked at this, for those of you who don't like me doing that, look at this. If I said, oh, no, look, that 3 is attached to the x, that'd be a horizontal stretch of 1/3, wouldn't it be? So a vertical stretch of 1/3 and a horizontal stretch of 1/3 actually are the same thing, okay? And that has to do with the symmetry of a rational function, okay? Cool. So we're going to say I have a vertical stretch of 1/3, and I'm going to go down 5. So that's a vertical translation, 5 units down, okay? So my vertical asymptote won't have changed. So that'll still be at x equals 0. But my horizontal asymptote now moves down 5 units. So that'll be at y equals -5. Okay, so my graph should look something like this. Okay. And now the description of the transformations, I just said, we have a horizontal stretch by a factor of 1/3 about the y-axis and a vertical translation 5 units down. So I wrote it as a horizontal stretch this time because it was attached to the 3. If you wrote it as a vertical stretch because I told you 30 seconds ago that we're only going to deal with A, I'm happy. It's okay. Okay. Don't freak out. All is well. The domain. Well, x is a member of the reals, but it can't be 0. And the range would be y is a member of the reals, but it can't be -5. Okay, and then again, my equation of the asymptotes, I have a vertical asymptote at x equals 0, and I have a horizontal asymptote at y equals -5. Okay? Okay, now we are going to take you down a trip down memory lane here, and we're going to talk about long division. So like long division was what you learned on how to divide numbers together before they let you use calculators. And I know it's still taught in schools, but I think sometimes it's taught like for a day, and then teachers are like, okay, now just use a calculator. So we want to convert. We want to convert to the form y equals a over x minus h plus k. Sometimes the rational function we're looking at doesn't look the way we want it to. Okay, so dividing will actually convert the form into a form that we can actually read better information from. So in order to do that, I'm going to practice with just numbers for a second to kind of warm you up. And we're going to take 321 and divide by 5, okay? So when we take 321 and we divide by 5, we would set it up like this. The 5 goes on the outside, and then the 321 goes on the inside. The name of the game is I'm always starting at the left, and I want to try and get rid of the left. So my first question is, how many 5s will fit into 3? And the answer to that is none. I should change the color of that. Okay, sorry. How many 5s fit into 3? The answer to that is none. So now I go, okay, how many 5s fit into 32? The answer to that is 6. Now, 6 times 5 gives me 30. So I've taken care of 30 of that 32. So I subtract and I get 2. Drop the 1 down, and now I'm left with 21. And I say, how many 5s fit in 21? And the answer to that is 4. And then 4 times 5 is 20. And then I have a remainder of 1. Okay, and so watch very closely what I'm about to do. I can say that 321 divided by 5 is 64 plus a 1 that never got divided by 5 yet. So it's still 1 divided by 5. So it's 64 and a fifth. Okay. Now, for those of you trying to piece this together and you don't want to just, memorize an algorithm, which I agree, you should never do that. This 30 is actually, like, what you were really doing here was how many 5s fit into 320. And so when you go 6 times 5, that's really thinking about like 60 times 5, which would give you the 300. We're just ignoring those zeros. Okay. So essentially, you're breaking it into 300, and then you deal with the 21, if that makes more sense to you. Okay. But what's really important to me is that you understand what's going down here, because if this was a polynomial, what I want you to notice is that looks like that. Okay. And so we end up with that k value, and then the remainder is actually the a over the x minus h value. Okay. Okay, so let's try it with polynomials. Just so you've got an idea here of a division statement, this is what I just did with you. So n of x over d of x equals q of x plus r of x over d of x. Don't shut down. Each one of those are just pieces of what we just did. N of x was the dividend, d of x was the divisor, q of x is called the quotient, and r of x is called the remainder. Okay. Okay. So we're going to take the same technique now and apply it to our rational functions. So I want to take a look at this, and what you want to notice is, hey, I don't see this in the form a over x minus h plus k. So let's get it in that form. I just have to do that division. It says 4x minus 5 divided by x minus 2. So the x minus 2 goes out on the front, and the 4x minus 5 goes inside. And now I'm working left to right and I'm trying to eliminate. So the very first thing I want to say is, what would I put up here so that when I multiply by x, I would get 4x, so I could get rid of the 4x, okay? And the answer to that question is I would need a 4. So I put a 4 right here. Now, I want you to notice where I put the 4. I want everything to line up in very neat columns so I can see what I'm doing, okay? So I have an x column right now, and I have a number column right now, essentially. So because I'm dealing with a number, not an x, I stuck it in the number column of my answer. So now I have to multiply. So I go 4 times x minus 2. Well, 4 times x is 4x. And 4 times neg 2 is neg 8. And then, just like I did with the numbers, I'm going to subtract. 4x minus 4x is nothing, which was the purpose of why we started this, right? We wanted to eliminate that front guy. But then I've got, be careful with your negatives, negative 5 minus negative 8. Negative 5 minus negative 8 would give me 3. Okay, so now I can rewrite this as 3 over x plus 2, because the remainder never got divided, plus 4. Okay, so f of x equals, always speak in complete sentences. I didn't give myself enough room there. 3 over x minus 2 plus 4. This and this are the same thing. Okay, they are the exact same equation. But this guy, I actually can see the transformations. I can now say, hey, I've got a vertical stretch of 3. I'm going to move 2 units to the right, and I'm going to move 4 units up. So really, I'm taking the base function of y equals 1 over x. I'm going to stretch it. I'm going to multiply all my y values by 3. I'm going to move 2 to the right and 4 up. Okay. Now, I went a little farther. I said, convert the rational function. I should actually read the question I asked you. I just got so excited. And then we wanted to do the asymptotes. So I've given you the question, and now I've told you the asymptotes. I also got into a transformation conversation there just because that's fun. But we have a horizontal asymptote at y equals 4, and we have a vertical asymptote at x equals 2. This is how we algebraically determine the horizontal asymptote. Okay, so if I ask you to determine a horizontal asymptote, this is the sort of thing I'm looking for as proof of your communication, proof of your work on a test. Okay. Okay. Awesome, awesome. Let's try this guy. 2x plus 7 over 4x. 2x plus 7 over 4x. So again, that means 2x plus 7 divided by 4x. So the 4x goes on the outside. 2x plus 7 comes on the inside. What do I put up here so that when I multiply by 4x, I will be able to get rid of a 2x? Well, I need a half. A half times 4 gives me 2, right? So I'm going to have a half up here. A half times 4 gives me 2x, and then that will give me a remainder of 7. So now that means I can rewrite this guy as 7 over 4x plus a half. Okay, 7 over 4x plus a half. So that means I have a vertical asymptote at x equals 0, and I have a horizontal asymptote at y equals a half. Okay. All right, x minus 2 over 2x plus 4. Again, I'm just trying to get you comfortable with this long dividing a polynomial. So 2x plus 4 goes on the outside, x minus 2 goes on the inside. What do I put up top so that when I multiply it by 2x, I end up with the x? I'm always trying to eliminate the left side, okay? And I'm working my way left to right. So what do I put up top? I'm going to put a half, because a half times 2x would give me the x that I'm looking for, okay? So 1/2, a half times 2x is x, a half times 4 is 2. Then I subtract x minus x is nothing, and negative 2 minus 2 is negative 4, okay? And so that gives me negative 4 over 2x plus 4, and then plus a half. So I have a, just think about this for a second. I could factor that 2 out. So that'd be 2 bracket x plus 2. So I have a vertical asymptote at x equals -2 and a horizontal asymptote at y equals 1/2. Okay. Awesome. Okay, so now in our last example, I've got f of x equals 6x squared all over 3x squared minus 7. So that's 6x squared divided by 3x squared minus 7. So 3x squared minus 7 is on the outside, the 6x squared is on the inside. And I'm asking myself, just like I did for the other examples, what do I put up here so that when I multiply it by 3x squared, I get out the 6x squared? Well, I would need 2, right? 2 times 3x squared gives me 6x squared. So I stick a 2 up there. When I do the multiplication, that gives me 6x squared minus 14. Now you got to be careful with this guy. This is like a 0 here, right? So if I go 0 minus -14, that actually gives me a remainder of 14, right? 0 minus -14 would give me positive 14. So I'm looking at 14 over 3x squared minus 7, and then plus 2. 14 over 3x squared minus 7 plus 2, okay? So that gives me a horizontal asymptote at y equals 2 because I moved everything up 2. And then it gives me a vertical asymptote. I just set that bottom equal to 0. So 3x squared minus 7 equals 0. I add 7 to both sides. I divide both sides by 3. That gives me x squared equals 7 over 3. And so then when I take the square root of that, that could be positive or negative. So I have 2 vertical asymptotes at x equals plus root 7 over 3 and negative root 7 over 3. Okay, awesome. All right, so that's where we're going to stop for now. We'll pick it up here together with the next lesson, but I've given you your homework. And if you have any questions, please make sure you connect with me. Okay, have a fantastic day. See you soon.